Okay, I'll just, I think everybody's here, so we'll just continue. Back to state agent mode. So, what you can also do is you can make a GG core plot, and that basically makes a plot of all the correlations of those 20 things. So in your case, it would be less. But what we did in this little bit of code is we load a package called GG core plot. I need dplyr as well, and the reason I need dplyr is for manipulating some data. So I make a correlation matrix, and core, as you might remember, was what we used for making correlations. So it doesn't do the correlation test, so it doesn't give you the p-value, it just gives you the actual correlation. We take the f data and we do it between 1 and 20. And we take the absolutes because we're only interested in the strengths of the associations. So in this case, we're only interested in the strength of the association, we're not interested in the direction. So that's why it will be absolute. So that's the abs there. And so then we take this object core matrix, we do the change the order, and then we wanted just lower column, and then we can do a method as well, which is not fully printed there, but you can see it in the .rmd. But basically, you can, just to show you can make a pretty picture where it basically visualizes the strength of the association between the things, like the size of the bubbles and the color of the bubbles indicates how strong the relationship is. So, not surprisingly, if people are very outgoing, they're also very talkative. They're associated with shy, but that's not in blue because it's negative. So if we had removed absolutes, then it would be a blue shade. But now, because we're just looking at the strength of the association with variables, shyness is associated with outgoingness variable as well. Yeah, but it could be coded in the opposite way. But just to keep everything the same color and not to have blue and red on the same thing, we just use the absolute. So this will also allow you to already see which things sort of go together. And ideally, before you do any type of analysis, the KMO test will do this, but this will also visually show you that there are associations in your data. If you only get really white things, like in this with white things and like tiny bubbles, then you have a problem. Then likely you're not going to get very nice factors out of it. Okay, I give you, as usual, I have to give you some further terms. You can also click that link. So basically, a factor is what we use to describe the underlying construct. So again, think of personality, neuroticism, openness to experience. That's the underlying factor. And you should also remember that these are not unique, and so you can basically rotate things to get a different solution. So it's so there's a little bit of trickiness to it, but so basically you first extract the factors and then you do some type of you can think of it as in 2 dimensions. You can still think of it as a space where you put things at the extreme. But factor analysis is basically doing this with 20 dimensions in a matrix, and we're rotating that matrix to get the most orthogonal or the most extreme solution, so to speak. So that's mostly just stuff for you to read in terms of terminology. You can read more about the maths, but you should know that factor is the thing we use to describe the labels of the latent constructs. There's also factor loadings. This is the degree to which an item contributes to that factor. So the degree to which a question on openness contributes to that score of openness. And so conversely, you could say to which degree is the openness driven by that single response on that item. What we can also get is, so factor loading is not the same as a factor score or a factor weight, but basically once we've done this, we can basically for every participant get a weight for openness or for neuroticism or some other measure. And basically you then want to use that score, for example, to correlate to something else, like their health or something else. And then finally, you have a measure. You have something called commonality of variable. It's the extent to which the variability across participants in a variable is explained by the set of factors extracted in the factor analysis. And you can also have the opposite, which is uniqueness, and that's 1 minus commonality. And that's just something which is typically reported, or you will see in the literature again. Again, these are terms I have to tell you because your supervisor will use them, or you will come across them in articles. So What I will now do is we'll get our very first factor analysis going, and again it's done via the site package, and we're going to get a large number of factors. We're just going to go and get 8, and then we're going to trim it down further. And the code is like this, so we make an object which we call FA for factor analysis. FA is the command. This is the data frame it takes. This is the number of factors. And then the factor method, I'll return to that. There's many different ways in which you can do factor analysis. MinRes is one of the most commonly used ones. I'll give you some other examples later on. And then how to rotate those things, because again, you can rotate it in different ways, and it's not going to change the type factor you get, but it might change the interpretability of the factors. So Varimax is again a commonly used one. And then that last bit, FA, means factor analysis, because you could also have principal component analysis. So the differences between those things are not too great. Okay, prepare yourself for a massive amount of output. So what I've done again is I've made a sync. So I'm going to put everything in a text, and then we're going to look at that text file. That should hopefully be it. So lots of stuff, right? So here we have all our items. We have MR1 to MR8, but they're rotated, so MR8 might be in position 3, but we have extracted 8 factors. So every single thing is giving you the loadings on each of those factors. So for example, distance loads on this factor positively 0.6, yeah, on the very first factor. And so you can basically look at all those 8 factors across, and for every single item, find the factor loading it's loading on that particular factor. The H2 and the U2, so that's here we have commonality, and that's a measure of unicity and a measure of loading as well. So don't worry too much about them. What we care about most is like how much variance do they explain. So these are loadings in terms of eigenvectors, but this is basically the proportion of variance and how much additional variance do you explain. So the first factor explains around 14%, and then we get another 9, another 8, another 7, another 7, another 7. And so this one is just summing it like cumulative 14, 23, 31. Proportion of variance explains if you take all the factors to add up to 1. So that's just rescaling it to 1. You can see if you assume that there's 8 factors and they explain all the variation, then the first one will explain 24% of the variance. Yeah. So you have some statistics, and then lots of stuff. We'll come to some of these measures later on. So, but there's some measures of fit indices like chi-squares and root mean square residuals. I'm not going to go into too much detail for them now, because we'll cover them again when we talk about confirmatory structural equation models or confirmatory factor analysis. For now, you just need to know that these are fit indices and that they might indicate how good or how bad your model is fitting. So this is actually quite good. So this should be close to 1, and the RMSEA is a measure of fit also, and should be close to 0.05. That's also good. And so basically, this is also the correlation between factors. So you can see if some of the factors are related to one another. So lots of output for you to work through and to see, but the key thing you want to be looking at is how much variance do the first couple of factors explain, and what do they actually look at, like what do they load on. And if we go back and look, we'll also do that in more detail later. You can see the first thing, for example, loads quite strongly on being quiet, being distant. What else do we have in here? Negative with talkative, so 0.76 negative with talkative. So likely it's tapping into some measure of introversion. Yeah. And so for every single one of those, you could then have a look and see this taps into laziness, discipline. Is there anything else which pops up? But especially that one is quite a high loading, and the discipline one is also quite a high loading. So likely that taps in here. Hardworking. This should be conscientiousness, or yeah. So tapping into. So all these items tapping into. So likely we should recover something from those adjectives which closely resembles the big five. So you can go through them and look more closely just by looking at the factor loadings. Again, I'll do one more. I can already give it away. So this one is agreeableness. You can see 0.71 loading on agreeableness. And if we go further down, let's see if there's another big score here. Cooperativeness, or being cooperative. So again, you should be able to label all those things after you've extracted those and try to make sense of them. Yeah. So lots of output to digest. I'm not going to go into too detail because we have several lectures just on this on your own. For now, you need to know that these are factor loadings that you care to how much factor variance is explained by them, and there's some measures of fit following that. And I'll talk to you a little bit more in detail now about them. If we go back. So massive outputs. So now the big thing is, how do we determine the number of factors? I just extracted a large bunch, but I could have also done 5 or 4 or 3. So there's several ways in which you could do it, and over the years people have proposed many different things. So you could say extract factors until the chi-square of the residual matrix is not significant. You could extract factors until the change in chi-square from factor n to factor n plus 1 is not longer significant. Extracting factors until eigenvalues of real data are less than the corresponding data. So this is known as parallel analysis. Plotting the magnitude of successive eigenvalues. And then, so this is eigenvalues 1, which might ring a bell from when you did it last time, which is quite a common criterion. And you could sort of think of it as a mountain, and you can see where their bent is to see where you're going to stop collecting factors. There's more, so lots of people disagreeing in many different ways. You could say you can extract factors as long as you can put names to them. That's also a rule you could use. So as long as I can keep naming these personality factors, we can use them. You can use a very simple structure criterion. You can use the Velociter minimum average partial test, or you could extract principal components or factors until the eigenvalue drops below 1. So many different routes to do this. I'm going to give you a couple, and depending on your supervisor's preference again, or your referee, or your reviewer preference, they might go for one or the other. So in many cases, you'll get similar type of solutions, but everybody has their own preference. Each has advantages and disadvantages. 8, although common, is probably the worst. That's what the statisticians agree on. So this eigenvalue greater than 1, so stop if it drops below 1. That's usually the worst criterion. And yeah, it's information overload. And you can read a lot more in things. So people had arguments back and forth. And so you can read more in that text. And I'm just going to give you some examples and how to find them in your output and how to interpret them. Some of it is part of the output already, and we can do parallel analysis. So as you remember, that was one of the options, and that's a fairly good one. Extracting factors until eigenvalues of real data are less than corresponding from random data of the same size. So basically, the idea is you simulate data. And if that noisy data set also gives you lots of significant factors, then you have a problem, and you're just cobbling together noise. Yeah. So this is the parallel analysis. So we call it parallel, and now the only difference is fa.parallel, and then the data factor method, and we have to say it's factor analysis. And then you get this type of plot. You have the factor analysis in blue for the actual data. And then you have simulated resampled data, but you can't really see the red dotted line because it's so small. But resampled means from the same thing, so resampled from the same type of data. So you can think of it as a sort of bootstrapping type of way. And so here it starts cutting over. So yeah, everything above this line is sort of found good. So you could say 1, 2, 3, 4, 5. So 5 factors, because otherwise you start overlapping with this. And so you can see this line here is the eigenvalues 1 criterion. Yeah? So you would have taken 4 or perhaps 5 if you still put it at 1, because that square is really on thing. So if you would be really strict, that's probably, I'm not sure if it's below or just on 1. but we can have a look at later. So for this one, just follow the blue line and sort of see where it touches the red. The Kaiser criterion. So this is the eigenvalues larger than 1. This is the worst, but it's still the most common. We can actually, from parallel, get the factor analytic values, and actually it just is indeed scraping by, so it's slightly higher. So that triangle you saw is slightly above 1. So those, if you go back, this is 6.51. So those values map on to what we have in our chart: 6.51, 3.63. So those values map onto this answer. So this is basically a plot of these Kaiser criterion. So this would also suggest 5 factors. Yeah. Now we can also look at the scree plot. So that was a really big mumbo jumbo about the mountain and being able to see the bend. Yeah. So this is where it sort of twitches. You would either do 4, depending on whether you think that's the whether this is the bend or that is the bend. I'll be somewhat lenient in interpreting your factor analysis as well. But if you say 2, for example, based on this graph, that would be wrong, because we can still see there's a further downward slope. But I'll apply to some degree. It sounds bad, but this is more art and science. Looking at these graphs, so I'll apply some range of flexibility. Okay, so we can get all that from that single chart. So we can get this is known as the scree test or the scree criterion, where it's basically looking at this elbow. We had the Kaiser criterion, which was eigenvalues larger than 1, and we had the parallel test. Now the very simple structure test, the VSS suggests 3 factors. So this is VSS fit. There's 2 ways of doing it. There's VSS 1 and VSS 2. I'm not going to go into too much detail, but you can see you get very little improvement over 4 actually this time, I think. So, and what you can do is just see. So this one, you can see basically factor 1 and 2, and so you can basically see. 1 would mean we've explained everything, how much gain you have from adding that additional 1, yeah, and see how the line goes up. So we don't gain that much from adding 4, and it doesn't even plot 5 or something, because it's not adding that much more. Yeah. Lots of things looking at lines and charts. Now the MAP test, so the Vellicer average partial test, that's printed to the output. And I didn't show it here because when I make the slides, it will show the graph but not the output. So VSS complexity, it says you can go up to 5 until you reach that 1 line. So it will also print you in verbal things what you see in the graph. But it says it's more reasonable to think of 3 factors. Yeah, that was what I was saying. If I go back to this line thing, you don't gain that much more from adding 4 to it. So this criterion would say stop roughly at 3. Although you could add, even though it's not really clearly showing things, the output will say what's going on, and the output says you can still gain a little bit by going to 5. So this is although VSS complexity 1 and VSS complexity 2 is so you can do it in 2 ways. These calculations. Again, you can read more. There's so much stuff going on, but just for you to compare. But in this case, it also gives you 5 factors. But more reasonable to think of 3 because we don't gain that much 4 from adding things. The Vellicer map is not graphically plotted, but that has 6 factors. And then you have some other measures like the BIC, which also says 6, and then there's a sample size adjusted BIC, which gives you 8. So depending on which criterion, so this is the Gardner forking patch, depending on what you pre-specified. So that's why it's usually also quite important to agree upon what you're going to do, which measure you're going to take. There's not that much difference theoretically between some of these. I wouldn't suggest you take the Kaiser's criterion, like this eigenvalue is larger than 1, because that will nearly always give you a surplus of factors. But this is where you sort of get different conclusions depending on what you picked. Now, we're going to do it ourselves. So I would like you to do a factor analysis on the Sedanius data, as I did. I'd like you to extract a large number of factors, 6. And I would like you to discuss the output with your neighbors, and then run a parallel analysis and just look at the chart. So we're not going to do all the other things. You can practice them also in the exercises, but just factor analysis with 6, and you can then run a parallel analysis and again discuss the outcome with your neighbors.